I will start with some general overview about the tools and plugins, and then I name the languages and libraries which were used. By this you see what I've programmed by myself and where I had to use libraries. After that I go more in detail, so I'll talk about my implementation, the development, and I'll show you diagrams to my architecture and explain for what the different classes are needed. At the end you will get also live preview with some general talk about the algorithms and features. I'll start with the tools and plugins. My integrated development environment I have used was PHP Storm. That's a commercial, but it's free for students and it runs great under Linux and Windows. The main debugging was done in Chrome. And for unit testing I've used JS Test Driver. That's a small Java program originally developed by Google some years ago, and today there exist several plugins for common IDEs like Eclipse, NetBeans and PHP Storm. And now let's look on the languages. For the interfaces I've used HTML5 and CSS3 like patterns, so I've used divs for the layout, and I've used also HTML5 tags in the drop-down menu. And for programming I've used only the current fully browser-supported version of JavaScript, so JavaScript based on the specification from 2011, so this ECMAScript 5.1. That was needed to get high compatibility with all the browsers, but because of this I had to simulate Java-like classes, because this version of JavaScript did not support it, and the simulation was done with a small namespace library called namespace.js. I will go more in details about that library on later slides. But now let's talk about the other libraries which have been used. jQuery to traverse the HTML code, Knockout to create dynamic user interfaces, especially the dynamic matrices you will see, and I had also a library to draw phylogenetic trees and a library to create downloadable files. Now let's go more in details. First I'll talk about my object-oriented implementation, then the development and the architecture. I've designed my part of the RNA-Playground project to be fully object-oriented. That was needed because I've got a lot of JavaScript files, and at some point I would possibly get name clashes between variables, and that I wanted to avoid right from the beginning, and therefore I've used this namespace library, which also allows me to write proper Java-like code. So what the people usually do is they separate their JavaScript functions with commas, and this makes the code less readable, but this is no more needed if you use that library. Here's an example. I first create a scope for my namespace, and then I give the namespace a name. The green string here, Needleman-Wunsch, and after that string I list all the static functions, so functions which should be visible outside the namespace scope. And usually the only function there is the constructor, because we have to create an instance of that constructor, and so it should be visible outside. Further below we can now define the constructor and do inheritance inside the constructor by creating an instance of the superclass, here alignment, which is in the namespace basis.alignment. And after we have this alignment instance, we can inherit the function, for example, setLinearAlignment input. and we rename it to set input in the Needleman-Wunsch instance. And this is now a public function because it's defined through the this keyword. But every other function like this function A is a private function because it's not defined in the constructor. But getSuperClass is again a public function because it's defined through the this keyword in the constructor. So you see everything you know from object-oriented languages like Java. I tried to simulate somehow to make the extension of the project as easy as possible. But I've done more. For me it was really very important to have fully correct implementations, also because hopefully a lot of students will use them. And so I wrote more than 50 unit tests with step-by-step PDF files. On the right side you see an example. You see an excerpt from the Tea Coffee unit test PDF file. You see it's very detailed, and I've implemented really every sub-step of that file with JS test driver. So I wanted to make, for somebody who does not know what I've implemented, the comprehension as easy as possible. Okay, and now I want to talk with you about my architecture, and first about the loading. On the top left you see a drop-down menu, and I choose an entry out of it. So for example, go to local. And if I do that, then the algorithm name is sent to the loader, and the loader has a function, update document view, with two arguments, the algorithm name and the view, so the div in which we want to load the algorithm page, so the HTML page into. How does it work? Update document view translates the algorithm name into an HTML file name and the JavaScript file name. And then it loads first the HTML file and then the JavaScript file. And that what you see here, that's the recombed way of loading, so you won't get any warnings. You see every algorithm page, it has an own HTML file and a JavaScript file. And to avoid a mixture of algorithm and interface logic, I have separated the interface logic, so the input and output logic, from the algorithm. So functions like sorting tuples are stored in classes, which I have called interfaces. There is a mother interface called interface, and it stores all the functions which are shared between all interface classes. It has two childs, the align interface for align algorithms and the clustering interface for clustering algorithms. What is the task of the align interface? It fills the tables of the output. So for example, if we have a Needleman-Wunsch matrix like the one on the left, then this matrix gets its values from the alignment interface. And the alignment interface, it has three childs which are defining the input. You will see it later on. And there are two more classes, the input processor and the visualizer, which are working strongly together and with the interfaces. And I will now talk on the next slides about these two classes. The input processor processes the input, and it is forwarding input and output. So for example, if we have an HTML input field like this one on the top left, then the input processor, for example, removes all bad characters like this. And then this data together with other data is sent in an object called input view model to the algorithm, and this algorithm retrieves the input data out of this object and computes the output data of the algorithm. The output data is then back sent to the input processor, which is sending this to the interface, which can do something like a post-processing. So for example, it can round all the matrix values, and afterwards it's displayed on the view, so on the HTML page. And now I said that the input processor and the visualizer are working strongly together, and that I want to show you on the next slide. So for example, we have a results table with all the results which are coming from the algorithm. And what happens if I now click on an entry in that table? Then the input processor is retrieving the table, so this results table and the row number, and is sharing it with the visualizer. And the visualizer can now highlight the entry in the table, and also it can highlight the corresponding traceback in the dynamic programming matrix on the right side. The question is now, what is the big advantage of using such an architecture with an input processor? First, it makes everything complex, but it is very efficient and modular. So you see the system consists out of different classes. I make an example. So I've said in the beginning that I use jQuery to traverse the HTML code. So you can write your HTML code like a tree and then do something like a depth-first search. And this is more or less how jQuery is working. But this is very inefficient, especially if you have a big website and do it multiple times. And the idea of the input processor is now that you search for the HTML elements your algorithm needs to only once and then reuse them. So here's an example. The input processor tells jQuery, search me the elements my algorithm needs to. And then jQuery is retrieving these elements and it is sharing them with the bindings, so the different events. And you see that's very efficient to share them. And I've designed the input processor such a way that the input processor is the only class which is allowed to execute jQuery code. And I had only 2 or 3 exceptions where I had to use jQuery out of the input processor. And the first exception was the drop-down menu, which is only available on GitHub in the offline version. And the other exception is the redrawing. So whenever I redraw cells or phylogenetic trees, I have to use jQuery. But there was no other clean solution. So I'll try to be very consequent in my architecture. Okay, and now I want to give you also a live preview. So let's switch to the offline version. Here, that's my drop-down menu. And here I can choose an algorithm. And now let's zoom in a bit. And I have implemented 12 bigger algorithms. You see in the list only 11 because agglomerative clustering here on the top. It consists out of 5 different sub-algorithms, UPGMA and the closely related one like WPGMA, but also Neighbour-Joining, which is very different. And their first algorithm I want to show you is Goto. That's a small algorithm but very interesting from its implementation. The algorithm pages have always the same structure. We have at the top some description with the author and the name, and below the input, and further below also the output. And here we can type in the sequences, and here we can change our scoring function. And the length of the sequences can be arbitrarily long, so we can type in something. and if it's too long, then we get a scroll bar and can scroll through the traceback here. Here is this results table you have seen before. Here we can change the alignment and get here on the left side the resulting traceback. Here we can download also the tables as comma-separated value files. And another interesting feature I want to show you is this here, the live update of the formulas. So if we, for example, change the enlargement costs, then it will also change automatically here in these formulas. So here -5, and can also, instead of maximizing the similarity, also minimize the distance. Then we get here a min instead of a max. So, and you see also this value here in the scoring function has been negated. So again, that's needed to get again the same tracebacks. And the main feature I wanted to show you is this here, the traceback arrow between two tables, how it is drawn. I didn't use HTML canvas, I've used scalable vector graphics. So I wrote me the XML code for scalable vector graphic and placed this as an overlay of the three tables. It has the advantage that SVG, it is very well documented. I can use the full SVG standard. I can change, for example, the style of that arrow, make it bold or dotted, and so on. And it also works on all smartphone browsers. Now let's look on the next algorithm, tCoffee. Here you have much more to read, and the input is also a little bit longer. Can also add here a local library, and the output I will discuss after I've showed you some nice feature. Here you can add or remove sequences, and let's add a sequence. So the cat, and you see it updates immediately. So here we get already the final result. And we have also extended the algorithm. So the original algorithm, it looks only on one alignment per sequence pair. So this algorithm computes pairwise alignments, and only one is considered. But we have extended it so we can consider more than one optimal alignment to create the libraries. And we can also add the local library, and here we can also change all the parameters. We can change also here the the total number of alignments, so for example 5. Then the best 5 local alignments are used to create the library. Here on the bottom you see all alignments, and you see only the 5 best local alignments are used to create the library. So yeah. Further here, further on the top you see the libraries. So here you see the sequence pair, and here the position, the aligned positions here, and here the values for the aligned positions. Here the primary library value, and here the extended library value. And you see everything is sorted, so I have to program this by myself. And you see also the tuples are also sorted alphabetically. And here you see also the phylogenetic tree, which is used for the Feng-Doolittle part of the algorithm, so for the merge steps or fusion steps to create the multiple sequence alignment. And further on the top you see also the final multi-sequence alignment. Let's now also look on the unit tests. So let's switch to PHP Storm, and here I have opened up the Needleman-Playground project, and under JS tests you find all the unit tests I have written. To execute them there is a file on the bottom here, unit tests, and here on the top you see all the imports that your test files using, and here you have your test files. And now to execute this test files you have just to run this file, so run unit tests, and then we have to click here and a browser window will pop up. And afterwards you see here that all the unit tests have passed, and to execute this file again you have maybe to stop your JS test driver server first. So under view, JS test driver server, and now we have to stop it, and then we can run this file again. Okay, thank you for watching. Here are also my sources.